Good afternoon all. Welcome to the lecture of discrete mathematical structure. Okay, so in last lecture we have seen what is an union of a set, intersection of set, complement of a set, difference of a set. Okay, and after that we have seen what is the symmetric difference of set. Okay, so today we will continue it. Now there are some algebra of sets. Laws of algebra of sets. Okay, that is there are some properties. Okay, now let A, B, and C, A, B, and C are any three sets. Any three sets. Then first one, A union B equal to B union A, and in that A intersection B equal to B intersection A. Second one, A union B union C is equal to A union B union C. Okay, this one is called commutative law. Commutative law. And in that second one is A intersection B intersection C is nothing but A intersection B intersection C. This one is called associative law. Associative law. Third one, A intersection A equal to A and A union A equal to A. This one is called idempotent law. Idempotent law. Fourth one, A intersection B union C is equal to A intersection B union A intersection C, and A union B intersection C is equal to A union B intersection A union C. Okay, this one is called distributive law. This will be a distributive law. Fifth one, A minus B union C is equal to A minus B intersection A minus C, and second one A minus B intersection C equal to A minus B union A minus C, and this one is called De Morgan's law. De Morgan's law. And last one, let A and B are two subsets of a universal set capital X or U, then A union B complement is nothing but A complement intersection B complement. This dash is nothing but complement. We can write also this as A union B complement equal to A complement intersection B complement. And last one, and in that second one, A intersection B complement equal to A complement union B complement, or A union B complement, sorry, A intersection B complement is equal to A complement union B complement. Okay, so these are the six properties. That is actually these are the called the laws of algebra of sets, and we have to prove all these properties. Okay, let us see its proof. First one, solution. As we have given that A, B, and C are any three arbitrary sets, and first one we have to prove that A union B is nothing but B union A. Okay, so here we have to just use the definition of given union, intersection, complement, whatever it will be. Okay, and and that is the difference of two sets. Since here also we have to find out a minus b union c and a minus b intersection c. So we have studied already all these definitions in last lecture, that is union, intersection, difference, complement, symmetric difference. Okay, we have to use these condition, these definitions, and to prove this one. Okay, now first we will prove that a union b equal to b union a. Okay, let x be any element which is belonging to a union b, as x belonging to A union B. Then by the definition of union of two sets. What is the union of two sets? If A and B are two sets, then the union of these two sets contains, that is denoted by A union B, which contains the elements from either the set A or the set B. So as x belonging to A union B, which implies x belonging to A or x belonging to B, which is from definition of union of sets. Union of sets. Okay, now if x belonging to A union B, then x belonging to A or x belonging to B, and if x belonging to A or x belonging to B, then also it is belonging to x is belonging to A union B. Since here we have either x is belonging to A or x is belonging to B, then by definition of union, if x belonging to A, x belonging to B, then x is belonging to A union B. Therefore this one has a if and only if statement. Okay, x belonging to A or x belonging to B, this can be written as x belonging to B or x belonging to A. Okay, so either we can write x belonging to A or x belonging to B, or x belonging to B or x belonging to A. Both are the same things. If x is belonging to B or x is belonging to A, which implies x is belonging to B union A. Okay, so here we have taken one element x which is belonging to A union B, and it is again it is again in B union A. Then by the definition of subset, A is a subset of B if every element of A is an element of B. So here we have taken one arbitrary x which is belonging to A union B, and it is also the member of B union A, which implies A union B is a subset of B union E, which is from the first condition, that is if x belonging to A union B, which implies x belonging to B union. But this one is an if and only if condition, that is if x is belonging to B union A, then it can be written as x belonging to B or x belonging to A, and which is nothing but x belonging to A or x belonging to B. If x belonging to A or x belonging to B, which implies x belonging to A union B. Therefore also, and B union A is a subset of A union B, which is from just the definition of union of two sets. Okay, so here we know that one property, if A and B are two sets, A and B are two sets such that A is a subset of B and B is a subset of A, then A must be equal to B. Okay, this one we have already seen this property. So here A union B is subset of B union A, B union A is subset of A union B, which implies from this property A union B is nothing but B union A, and that is we have to prove, that is A union B equal to B union A, and hence the required example. Similarly we can prove A intersection B is equal to B intersection A. Okay, so in the same way we can prove this one. Now second one, this property is called as a commutative property. Now second one is nothing but to prove that A intersection B intersection C is equal to A intersection B intersection C. Okay, now let x is any element which is belonging to A intersection B intersection C. Okay, so we have taken one x which is member of this one, and this x will be an any arbitrary set, and if this property holds for any arbitrary x, then it is holds for all x belonging to A intersection B intersection C. Now what is the intersection of two sets? If A and B are two sets, then intersection of A and B contains all those elements which are common in both A and B. Okay, that is A intersection B is nothing but it contains all x such that x is belonging to A and x is belonging to B. Then by definition of intersection, which implies x is belonging to A and x is belonging to B intersection C. Okay, since x belonging to A intersection B intersection C, which implies x belonging to A and x belonging to B intersection C. And if x is belonging to A and x belonging to B intersection C, then it is again belonging to x A intersection B intersection C. Therefore, again it is if and only if statement, which is nothing but x belonging to A and x belonging to B and x is belonging to C. It is again since x is belonging to B intersection C, which implies x is member of both the sets B and C. Therefore, this can be written as here x is belonging to A, it is belonging to B, and it is belonging to C. Therefore, it can be written as x belonging to A and x belonging to B and x is belonging to C. Both are same, which is nothing but x belonging to A and x belonging to B, which implies x belonging to its intersection. A intersection B and x is belonging to C. And x is belonging to C. Again, it is if and only if x is belonging to A intersection B and x is belonging to C. As x is member of both A intersection B and C, then it is again member of its intersection, which implies x is belonging to A intersection B intersection C. So here we have taken one element x, which is a member of A intersection B intersection C, and it is again a member of A intersection B intersection C. Then again, by the definition of subset, here we have taken x, one x, which is member of this one, and we have proved x is belonging to this one, which implies A intersection B intersection C is a subset of A intersection B intersection C. But this one is if and only if statement. Therefore, if we take x belonging to A intersection B intersection C, then it is belonging to A intersection B intersection C. And A intersection B intersection C is a subset of A intersection B intersection C. Okay. So again, here A is a subset of B is a subset of A. Then again, by the property, if A is subset of B and B is subset of B is subset of A, then A must be equal to B, which implies A intersection B intersection C is nothing but A intersection B intersection C, and that is we have to prove. Hence the required result. And similarly, we can prove the associative property for union also. Similarly, A union B union C is nothing but A union B union C. Okay. Now third one. In third one, we have to prove that A intersection A is equal to A and A union A equal to A. But if we use the first property, that is A union B equal to B union A, then we obviously get A union A is nothing but A. Since union of two sets is nothing but it contains all those elements which are either belonging to A or B. As here union of these sets both are same, A and A. Therefore, its union contains only the elements of A. And similarly, A intersection A contains, by definition, it contains all the elements which are belonging to both A and B. But here B is nothing but A. Therefore, A intersection A contains all the elements of A. Therefore, from first property, it is trivially holds. It means trivially holds. Now, fourth one, that is distributive property. To prove that A intersection B union C is equal to A intersection B union A intersection C. That is we have to prove. And from that one, we will extend this to A union B intersection C is nothing but A union B intersection A union C. First, we will prove this one. Let X is any element which is belonging to A intersection B union C. That is the element which is belonging to this first set. Okay. Now X belonging to A intersection B union C. Let us consider this one as A and this total B union C as B. As X is a member of A intersection this B union C, then by definition of intersection, it is an element which is belonging to both A and B union C, which is implies and implied by X is belonging to A and X is belonging to B union C. And if X is belonging to A and X is belonging to B union C, then X belonging to both A and B union C. Therefore, it is contained in intersection. Okay. Now this can be written as X is belonging to A and now here X is belonging to B union C. But B union C, B union C contains all those elements which are belonging to either A, either B or C. Therefore, X is belonging to B or X is belonging to C. Therefore, this total can be written as X belonging to A and X is belonging to B, or X is belonging to A and X is belonging to C. Since these are the two possibilities here. Since here X is belonging to A and X is belonging to B, or X is belonging to C. Therefore, X is belonging to A and X is belonging to B, or X is member of A and X is member of C. These are the two possibilities. Okay, now X is belonging to A and X is belonging to B. As here X is an element which is member of both the sets A and B. Therefore, it is must be in its intersection, which implies X belonging to A intersection B, or again X is belonging to A and X is belonging to C, which implies X is belonging to A intersection C. Now here X is belonging to A intersection B, or X is belonging to A intersection C. Then by the definition of union, as here X is member of A intersection B, or it is member of A intersection C, then X is belonging to A intersection B union A intersection C. As here there is or, then by definition of union, it is nothing but union. So here we have taken one X which is belonging to A intersection B union C, and we get X is belonging to A intersection B union A intersection C, which implies the first set A intersection B union C is a subset of A intersection B union A intersection C. But this one is an if and only if statement. Therefore, its converse will be also true. That is, if X is belonging to A intersection B and union A intersection C, then it is belonging to A intersection B union C, which implies the second one is also a subset of first one. A intersection B union A intersection C is the subset of A intersection B union C. Okay, but here we get this one is a subset of this one, and this one is a subset of this one. Therefore, as A is subset of B and B is subset of B, A is subset of B and B is subset of A, then by the definition, that is A subset of B, B subset of A, which implies A equal to P. Therefore, A intersection B union C is nothing but A intersection B union A intersection C, and that is we have to prove, and hence the required result. And similarly, we can prove A union B intersection C is nothing but A union B intersection A union C. Okay, so here we have proved fourth one. Now it remains to put to the fifth property and sixth property. Okay, now fifth one. To prove that A minus B union C is equal to A minus B intersection A minus C. That is we have to prove. Now again let X be any element which is belonging to A minus B union C. Okay, so here X is an element which is belonging to this difference of two sets A and B union C. Then by the definition of difference of two sets, if A and B are any two sets, then A minus B contains all those elements which are belonging to A, but they are not the member of B. As here B is nothing but B union C. Therefore, X belonging to A minus B union C contains all those elements which are members of A, but they are not the member of B union C, which implies X is belonging to A and X is not belonging to B union C. Okay, and if X is belonging to A and X is not belonging to B union C, then it is which implies X is belonging to A minus B union C, which is again by the definition of difference of two sets. Therefore, it is if and only. Therefore, it can be written as X belonging to A, and as now here X is not belonging to B union C. That is, X is not a member of B and C both, since B union C contains all those elements which are either the members of B or C. But here X is not a member of B union C. It means X is not a member of B and it is not a member of C. Therefore, X is not belonging to B and X is not belonging to C. Therefore, this can be written as X belonging to A and X not belonging to B and X belonging to A and X is not belonging to C. Okay, now it is if and only here X is belonging to A and X is not a member of B. Then by the definition of two sets, difference of two sets A and B, A minus B contains all those elements which are the members of A and which are not the members of B. Therefore, as here X is belonging to A and X is not a member of B, which implies X is belonging to A minus B, and X is member of A and it is not a member of C, which implies X is belonging to A minus C. Therefore, as X is member of A minus B and it is member of A minus C, both it is member of both the sets A minus B and A minus C. Then, by definition of intersection of two sets, X is belonging to A minus B intersection A minus C. Okay. So here we have taken one X which is member of A minus B union C, and we have proved that it is a member of A minus B intersection A minus C. Then by the definition of subsets, A minus B union C is a subset of A minus B intersection A minus C. Okay, but this one is an if and only if statement. Therefore, as X is belonging to A minus B intersection A minus C, then it is member of A minus B union C, which implies A minus B intersection A minus C is also the subset of A minus B union C. Now, from again here we get A is subset of B, B is subset of A, which implies A minus B union C is nothing but A minus B intersection A minus C, and that is we have to prove. Here is the required result. Now, similarly, we can prove the intersection C. And here is the proof. Okay, now we have proved the fifth one. As now it remains to prove the sixth property, which is the another form of De Morgan's law. That is, if A and B are any two subsets of a universal set X or U, then A union B complement is nothing but A complement intersection B complement, and A intersection B complement is nothing but A complement union B complement. A union B complement intersection B complement and B complement equal to A complement union B complement. We will first prove this one, and from that one we will prove this one. Okay. Consider X is any member of first sets A union B complement, and we know that if A is any subset of a universal set U or X, then A complement contains all those elements which are not the members of A but they are members of U. That is, there is one definition. What is A complement? It contains all elements which are belonging to universal set A and they are not belonging to A. This one is nothing but A complement. Therefore, X is belonging to A union B complement. This implies that X is belonging to A union B complement. Then it means it is not a member of A union B, since it is a member of complement, and the if A is any set and A complement B its complement, then A intersection A complement is equal to 5. That is, there is no element common in between these two sets A and A complement. Therefore, as X is belonging to A union B complement, then X is not belonging to A union B, since complement and the sets are disjoint, since there is no element belonging to these two sets. Therefore, as X is member of A union B complement, then it is not belonging to A union B. So, as it is not belonging to A union B, which implies X is not belonging to A, and X is not belonging to B. Since X is not a member of A union B, then it is not belonging to both the sets A and B. Now again, by definition, X is not a member of A, which implies it is a member of its complement, and X is not a member of B, which implies it is member of its complement. Therefore, here we get X is belonging to A complement and X is belonging to B complement. Then by definition of intersection of two sets, X is belonging to A complement intersection B complement. Okay, so here we have taken one element X which is member of A union B complement, and we have proved it is member of A complement intersection B complement. Then by definition of subset, as X is member of this one, which implies X is member of this one, which implies first set A union B complement is a subset of A complement intersection B complement, and as it is if and only if statement, therefore A complement intersection B complement is a subset of A union B complement. Okay, So which implies A union B complement is subset of A complement intersection B complement. A complement intersection B complement is subset of A union B complement, which implies as A is subset of B and B is subset of A, which implies A equal to B, which implies A union B complement is nothing but A complement intersection B complement, and that is we have to prove, and hence the required result. And in similar way, we can prove A intersection B complement is nothing but A complement union B complement. Okay, so here we have proved all the six properties. Okay, now Cartesian product of two sets. Next definition. Cartesian product of two sets. Okay, so here we have to just take the product of two sets and we have to define how to write the product of two sets. Okay, for that we require at least two sets. Let A and B are any two sets. Let A and B are any two sets. Okay, so as here we have two sets A and B, then AB is called the ordered pair. Ordered pair. Okay, so if we have A and B are any two sets, then here AB is called the ordered pair, and the object A, sorry, small a, A, it's called the first coordinate of the ordered pair AB, the ordered pair AB, and the object B is called, that is small b, and the object small b is called the second coordinate of the ordered pair AB. Okay, the second coordinate of the ordered pair. Okay, so here we have two sets A and B, and the elements of the form AB is called the ordered pair, and the first element A is called the first coordinate of the ordered pair AB, and the object B is called the second coordinate of the ordered pair AB. If AB and CD are two ordered pairs, CD or two ordered pairs, then ordered pair AB is equal to ordered pair CD if and only if A equal to C and B equal to D. Okay, so here suppose we have two ordered pairs AB and CD, then these two ordered pairs AB and CD are equal if and only if A is equal to C and B equal to D. For example, the ordered pairs 2, 5 and 2, 5 are equal, while the ordered pairs 2, 5 and 5, 2 are not equal. Okay, so when we say that the two ordered pairs AB and CD are equal, if first element A is equal to C and second element B is equal to D, then only it is possible that the ordered pairs are same. So here we have taken 2, 5 and 2, 5, the two ordered pairs. As here 2 is equal to 2 and 5 equal to 5, then these two ordered pairs are equal. But here 2, 5 and 5, 2 are not equal ordered pairs, since 2 is not equal to 5 and 5 is not equal to 2. So 2, 5 and 2, 5 are the equal ordered pairs, while the ordered pairs 2, 5 and 5, 2 are not equal. Let us see what is the actual definition of ordered pairs of two sets. Sorry, Cartesian product of two sets. Okay, let us write actually definition. Let A and B be two sets. The set of all distinct ordered pairs, the set of all distinct ordered pairs whose first coordinate is an element of capital A, whose first coordinate is an element of A, of capital A, and the second coordinate is an element of capital B. Okay, so if we have two sets A and B, then what is the Cartesian product of two sets A and B? The set of all distinct ordered pairs whose first coordinate, ordered pairs means it is of the form AB, whose first coordinate is an element of capital A and the second coordinate is an element of capital B. Okay, and it's called Cartesian product of A and B, and is denoted by A cross B, and symbolically it is nothing but Cartesian product of A B is nothing but it contains all the ordered pairs A B such that A is belonging to capital A and B is belonging to capital B. So it will be the Cartesian product of two sets A and B, which contains all the distinct ordered pairs AB such that A is member of capital A and B is member of B. Okay. For example, suppose A and B are two sets having elements ABC and PQ. For example, let capital A is equal to ABC and capital B is equal to P and Q. P, comma Q. Okay, so here we have two sets A and B. First set contains three elements ABC and second set contains two elements P and Q. Then A cross B. A cross B contains all the ordered pairs AB such that A is member of A and B is member of C. Therefore, first take the element A, comma Q, comma A, comma A, comma P and A, comma Q. E, comma Q. Now second element B, comma P, B, comma Q, B, comma P, B, comma Q. Similarly, C, comma P and C, comma Q. So these are the distinct ordered pairs which are possible from these two sets A and B having elements are ABC and PQ. And similarly, B cross A is nothing but. Now we have to take the elements of B first. PA, PB, PC, QA, QB, and QC. Okay, so these are the possible distinct ordered pairs from B and A. But here we know that two ordered pairs A, B, and C, D are equal if and only A equal to C and B equal to C, B equal to D. As here there is an AP and here there is an PA. But A is not equal to P and P is not equal to A, which implies these two ordered pairs are not equal. Similarly, all the remaining ordered pairs. So clearly A cross B is not equal to B cross A. Okay, but if A and B are two same sets, then it is possible that A cross B will be equal to B cross A. Okay, so in general we can write A cross B is not equal to B cross A. Now if this set A has m elements and set B has n elements, then or Cartesian product of A cross B has m into n elements. Okay, so if we have two sets A and B, in first set A contains m elements and second set B contains n elements, then the product of these two sets, that is A cross B, contains m into n elements. For example, here we have taken A equal to ABC, which contains three elements, and B equal to PQ contains two elements. Then by this property, A into B contains 3 into 2, which is equal to 6 elements. This one is first, 2, sixth, third, fourth, fifth, and sixth. Similarly, B cross A also contains 6 elements, since 2 into 3 will be equal to 6. Okay, now second property, if A and B are any two sets such that either A or B is empty, then Cartesian product of A cross B is empty. Empty, or we can also write this one as a null. Empty set or null set. That is, this one also called as null set. Okay, so if we have two sets A and B, and any among these two sets, if anyone is empty, then its Cartesian product is again empty. For example, if suppose A be a set which contains the elements 1 and 2, and B be a set which contains no element, that is, it is a 5. Actually, we write this one as a 5, then it is a set containing one element. Empty set is denoted by 5. Now, if we find out A cross B, A cross B contains all the ordered pairs AB such that A is belonging to A and B is belonging to B. But here there is no element in B. Therefore, ordered pair, there is no possible ordered pair such that first coordinate is an element of A and second coordinate as an element of B. Therefore, A cross B must be equal to 5. Now, third property, if A and B are any two sets such that either A or B is infinite, and the other contain and the other is non-empty, then A cross B is an infinite set. Okay, so here we have two sets A and B, in which either A or B is an infinite set. Infinite set, it means it contains infinite number of elements, and the other is non-empty. Since if A is any set and B is equal to 5, then A cross B must be equal to 5. Then if we have to get A and B to A cross B to be an infinite set, then other must be an non-empty set, and one is infinite set. Therefore, A cross B is an infinite set. Now, there is one more definition: product set in general. Since here we have taken the product of only two sets, if suppose there are more than two sets, then how to take the product of these two sets? Let A1, A2 up to so on A and B n sets. Let A1, A2 up to so on A n B n given sets, the set of ordered n tuples, A1, A2 up to so on A1, A2 up to so on A n, where A1 belonging to A1, A2 belonging to A2 up to so on An belonging to An, is called the Cartesian product of Cartesian product of A1, A2 up to so on An, and is denoted by a1 cross into cross up to solve cross an. Okay, so we have already seen what is the product of two sets. That is, if a and b are two sets, then Cartesian product of two sets contains all the ordered pairs ab such that the first coordinate a is a member of capital A and second coordinate b is a member of capital B. But if suppose we have to find out the product of more than two sets, if suppose we have a1 a2 up to so on an be any n sets, then the ordered n tuples. N tuples means it is an ordered pair which contains the n elements. That is a1 a2 up to so on an, in which small a1 is belonging to capital A1, small a2 is belonging to capital A2, and up to so on small an is belonging to capital An, and is called the Cartesian product of these n sets a1 a2 up to so on an, and is denoted by a1 cross a2 cross up to so on cross a. Okay, so thank you for watching the lecture.